Okay, my computer is 11. Shall we start, Tommaso?
Okay,
Yeah.
yes, of course.
Okay, so this is the first the session on this is one of the sessions on the MacroFor section within the IAF, and the first speaker is Tommaso Proietti from Rome, and the title of his talk is Nowcasting the National Accounts with Big Data. So,
and can you see my screen, Pilar? Can
yes,
you see my slides?
yes.
Okay, very good. So, okay,
Yes.
thank you very much. And it's a great pleasure to present here. I'm presenting a paper which is a joint work with many co-authors, as you may see. Alessandro Giovanelli from the University of L'Aquila and Ambra Citton, Ottavio Ricchi, Christian Tegami, and Cristina Tinti. They both are, they all are at the Ministry of Economics and Finance in Italy. Okay, so our research problem is to estimate the components of GDP and GDP itself at the monthly level. And so our problem is nowcasting and forecasting GDP, essentially. The main components of GDP according to the expenditure disaggregation and according to the output type. I will say something about it in a second. So why that? Why do we need this? Well, we know that the national accounts provide a very comprehensive set of economic statistics with a high coverage and providing a very coherent and exhaustive description of the state of the economy. However, you know, they are available with a non-ignorable publication lag and only at the quarterly frequency. Now we want to make this frequency monthly, and we want to be we have a more timely assessment of this data while using this national account framework. Okay, so what we do is that we look at the disaggregation of GDP by component. Here is the decomposition by output type. And so we consider sectors of the economy and the contribution through value added to GDP at market prices. And we look also at the breakdown of GDP by expenditure type. So these are the two things that we look at. And so let me go back here. So how do we do that? Of course, this is a well-known problem. There's a lot of literature about it. And what can be said that is new? Well, we think that we have our own way of going about this. So let me frame the problem and let me describe what we are doing by introducing some notation. So we are interested in YIT, which represents the monthly value of a component of GDP or GDP itself at time t. And t is measured in months, right? We have 16 GDP components plus GDP, and this is not observable at the monthly frequency. It's observable only quarterly, which is capital YIT. So it's observed only quarterly. There should be actually a tau here, but you know, it's observed only quarterly and with some publication lag. So what we would like to do is to project the our estimates of quarterly GDP on a set of monthly indicators. And in particular, we will be concerned with the Italian case where we have 500 or so, 433 monthly indicators. And we would like to use this information to produce our estimates of the components, our nowcast and forecast of the components and GDP itself. We shall denote by capital YIT the set of information available from the national accounts at any time t, and t will be time in months. And we will denote by with this chi JT the information available on the jth economic indicator. This is a monthly indicator available at this high frequency with some publication schedule, so that it's available with some delay, right? Which we call the delta J. So we are interested in projecting the unobserved YIT on the information spanned by this set of monthly indicators. This is what we do. So what we ultimately aim at is the projection of the nowcast and the forecast of monthly GDP and its components on all the available information. All the available information encompasses what is available to us from the Italian national accounts and from a set of monthly indicators collected and monitored by the Ministry of Economic Finance, right? So that's the full information set, and the monthly indicators provide, each one provides an information that the union of the information makes up the full data set. Now, how do we do this? We combine the partial projection along with using one indicator at a time, which we denote by this symbol. Right, so this is, I will say that this will arise from a bivariate model, right? So we consider all the possible projections carried out one indicator at a time. And then we combine them with some weights, right? So I need to discuss what model do we use to produce a monthly estimate of GDP and its components using one indicator at a time. And then how we combine them with suitable weights, right? So these are the two ingredients. And as far as the model for evaluating this partial projection, we use a model which takes into account the factor structure of the economy. Essentially, we assume that each monthly indicators participates of this factor structure, can be written down as, first of all, each monthly indicator will be assumed to be I1, integrated of order 1, which means that for nominal indicators such as prices, the CPI, and so forth, we will take the monthly inflation rate. And for business surveys, which are presumably stationary, then we integrate them to fit this representation. Okay, so we assume that the generic indicator is I1 with some drift component specific to the series and a common component here. So each indicator participates to the commonality by a common component, which is this chi JT, and psi JT would denote the idiosyncratic, the specific component to the indicator itself. So the common components of the monthly indicators span a common space, span the space of the common factors, right? And each indicator, which is here represented by a circle, has a common component and a idiosyncratic component. Now, our our GDP components and GDP itself will be projected on the space spanned by the common components of the indicators. And for this, we use a set of capital N bivariate models, as many as there are indicators, and the structure is very simple. So despite the algebra here, we assume that the generating process of each indicator is driven by a common component plus an idiosyncratic one, as we specified before. And the unobserved monthly component of GDP, or GDP itself, shares this common component of the J indicator, and this is the loading, right? Through this loading here. So also the component is I1, integrated of order 1. This is unobserved, of course, but it is driven by the common components of each individual indicator. And then you see all the rest, so the parts of the indicator which is not common, right, to the other indicators, so sorry, the complement to the common component of the Jth indicator is collected here. The effect of that is collected by xi it. So this factor structure of the economy imposes some restrictions on this model. And this model, can be easily estimated by linear state space methods, which I don't discuss here because I don't have time. So this is an unobserved component model driven by a common factor and can be dealt with by specific methods that relate to the linear state space framework. So I won't discuss this further. Now, a second issue is that, okay, now we have these individual projections. So we have n monthly estimates of the components, monthly estimates of the GDP components, how do we combine them together? What kind of weights do we use? Of course, you know, the optimal weights could be derived if this projection was stationary. And if we could derive the covariance matrix of the individual projections and the covariance matrix on the projections with the target variable. However, the target variable is not observed at the monthly frequency. And furthermore, these guys, the individual projections, are not stationary. So how do we do this? Well, we discuss how we can optimally derive the weights. And two strategies are considered. Essentially, we can derive the weights from the training sample. And so we use weights related to the likelihood, which is a conditional likelihood on the information set. And this is derived from the Kalman filter, since we use a sequential processing of the two variables. We process first the indicator, and then we condition on that, and we process the unobserved component of GDP. So we can derive these weights from the estimation within the training sample, or we can go out of the sample and then compute the variance covariance matrix of the prediction errors with reference to the quarterly GDP, and use that to derive the optimal combination weights, which is the usual formula. And the issue here would be how we estimate the sigma I. Sigma I would be the variance covariance matrix of the quarterly prediction errors of each of the individual models, arising from each of the individual models out of the sample, right? So how do we estimate this? Of course, you see capital N, the number of economic indicators, is typically as large or larger than the number of available observations. So the sample covariance matrix would be badly specified and ill-conditioned. So what we do is we take the Ledwine-Wolf shrinkage estimator, where we combine together the variance covariance matrix and the variance covariance matrix estimated with a compound symmetry covariance structure in mind, such that all the prediction errors share a common correlation, an equal correlation, are equally correlated. So this is a target that works better than other targets that we considered. So I will present the results only with respect to a compound symmetry covariance structure. So this variance covariance matrix arises from considering the sample covariance matrix of the prediction errors of quarterly GDP and its components, and lambda I would be the shrinkage intensity, and the sort of the shrinkage target would be this matrix such that all the prediction errors share the same correlation that can be estimated from the sample. And for estimating the optimal shrinkage intensity, we use Ledwine-Wolf's closed form estimator as well as a grid search and compare. Right. So the final issue, the final issue would be how do we combine the GDP components together? Now, we cannot sum the GDP components because we work with the estimates and nowcast and forecast that are at chain volumes, right? And we cannot sum up chain volumes estimate. We need to proceed by a nonlinear aggregation scheme, but we can get, so we need to deflate first the estimates so that they are expressed at the prices of the previous year. Then we can aggregate, and then we rechain back and produce the estimates again in chain volumes. This is quite articulate. I will not spend too much time with it. So let me finish with a description of our results. We have a data set consisting of the national accounts for the Italian case produced by ISTAT, and a collection of 433 monthly indicators. And this data set is strongly unbalanced towards the survey component, right? One merit of our approach is that we don't assume how many factors are there. We don't need to identify the factors. Each individual indicator will contribute to the estimate by sharing a common component, right? So we don't need to take a stance on the number of factors that are there. Okay, so our methodology can be used to produce historical estimates and the growth accounting. So we can produce a monthly GDP estimate in historical sense using the Kalman filter and smoothing equations, and look at monthly GDP aggregated according to the output approach by branch of economic activity and according to the expenditure approach. There are some nice differences between the two estimates. So for instance, the conditional mean estimate from the output approach is more variable, as you can see, is more as a more jagged appearance. This is because industry and trade are more, varying, are more volatile a little bit. From the expenditure approach, the conditional mean is smoother. However, as you can see from the confidence bands, the conditional variance is smaller from the output approach because the indicators are stronger for the output approach. For production, industrial production is a strong monthly indicator for value added in industry, for instance. We can do growth accounting. These are growth accounting, the contribution to the GDP growth of the various components from the output side. We consider the same scale here to point out that industry and trade are contributed more. And it's interesting to see also what is the contribution of the expenditure components, which is very strong during the sovereign debt crisis, as you may see. Not much is the contribution of the output components in that situation. It's the contribution is very strong during the Great Recession. So here you can learn a lot from this decomposition. Then we carry out a pseudo real-time nowcasting and forecasting experiment where we have 3 situations. At the end of each month, we nowcast and forecast GDP. And perhaps I have very little time here. So let me tell you what is the story. The story is, yes, the story is the indirect approach from the output side outperforms the other methods, and we outperforms the benchmark. And we have a wealth of information to assess what drives this result, what motivates this result. Why do we have a prediction accuracy gain from using the indirect output approach? Well, first of all, the gains are mostly obtained during the Great Recession and the sovereign debt crisis. And we can break down the contribution and have a variable importance measure. And we can break down the results. And as the information progresses during the quarter, we can reduce the uncertainty. And the role of the information changes. So in the first month of the quarter, for instance, the surveys are very important. They provide most of the accuracy. Whereas as we go along the quarter, hard indicators such as industrial production tend to show up. And as you see, when we are in the 3rd month of the quarter, then we use more the information on turnover, industrial production, on transportation across the rail and the motorway system. So that's the main result. We find out that there is evidence for carrying out indirect estimation of GDP. There is greater accuracy to be gained, and we can trace out what are the determinants of that. So sorry, I rushed a little bit in the end, but I'll be ready to take questions on that. So thank you, Pilar. That's all.
Okay, many thanks, Tommaso, and many thanks for the effort of finishing on time. Now we have a few minutes for questions for Tommaso. Also, you can pose questions.
Maybe I have a...
Yeah, go ahead, Luca.
Yes, Tommaso, so it seems that it's very interesting, the composition of GDP that you make, where you can see the contribution of all GDP components. And you are saying that very likely you are having you have a gain in the recession times, okay, in recessionary times.
Yes.
Would it be possible maybe to explore the contribution of each of these components a bit more rather than just using variable importance? So for instance, you have also methods that exploit that go and see, for instance, whether you have a nonlinear effect of that component with respect to that variable, for instance, partial dependency plots or local accumulated effects or things like this.
Yes, that's something that, so alternative measures, yes, they are most welcome. So yeah, the partial dependence plots, that's something we didn't try. We looked at what is the contribution to the weight, to the aggregation weight, and we looked at how many times we use that indicator for nowcasting, how many times it showed up in the top, say, top contributing indicators. So this is what we did. But that's surely something very important to look at the scale of the indicator itself and to look at the partial dependence.
Yeah. Any other questions for Tommaso? You can also pose questions through the chat. No? So if there are no more questions, we are going to move to the second speaker. The second speaker is Luca Barbaglia from the Joint Research Center of the European Commission. And the title of his talk is Forecasting with Sentiment Indicators in Factor Models. So go ahead, Luca. Luca, we don't hear you. You need to unmute yourself.
Okay, yeah, I'm sorry, Pilar. Do you hear me now and see my slides?
Yes, yes.
Okay, thank you very much. So the title of my work is Forecasting with Sentiment Indicators in Factor Models, and this is a joint work with indeed Pilar and with Filippo Pericoli. As Filippo and I are both working at the European Commission Joint Research Center, the usual disclaimer applies. So these are our views and not the ones of the European Commission. So this is a bit of a preview of what we aim to do in this paper. The goal is quite simple, using factor models as an nowcasting tool for the Euro Area 19 GDP. And we want to do that in real time. So we will use a real-time macroeconomic data set. And we want to build factors using three different data sets. One is a real-time macroeconomic data set that we get from the OECD. And then we will have survey-based sentiment indicators providing joint research. And then we'll have also news-based sentiment indicators that we built our own with a sentiment analysis procedure that I will present briefly during the presentation. So the idea is to make a nowcast of real GDP for the Euro Area 19 at different forecast horizons and see which one of these data sets can actually help in having a forecast gain. So digging in directly into the data, we have the macroeconomic variables that come from the OECD main economic indicators table. We have around 20 variables that are sort of the monthly and quarterly frequencies. Triangle as of February 2015. I couldn't find anything, any vintages older than 2015. I don't know if you have any experience working with real-time data in Europe, but if you have any suggestion where to find other type of data, well, I will be more than welcome to discuss it and to have an input from you. And the dependent variable that we want to forecast, as I said, is real GDP, which is of course quarterly. The second part, the second data set that we consider, as I said, are survey-based sentiment indicators published by the European Commission. These are business and consumer surveys made for the Euro area 19 about construction services industry. Indicators published at the end of each month, around the 20th day. And as I said, they are survey-based, so they come from a quite long and lengthy process of surveying businesses and consumers. So the idea is that it might be a very good predictor for monthly frequencies. However, they might not react so fast for unexpected shocks. And then we have the last part, the third data set that we consider, which are news-based sentiment indicators. We build these indicators following the procedure that we present in another data set, in another paper, which is forecasting with economic news, that was also presented by my colleague Sergio Consoli here at the ISF. So if you are interested in having more information about the algorithm, please check out his presentation on YouTube. I will now outline very briefly how our algorithm works. First of all, our algorithm for sentiment analysis is fine-grained, meaning that given a certain text, we are able to assign a score to this text that is between -1 and 1. And we do that using a dictionary that we built and that custom for economic applications. This dictionary is essentially a human annotated version of the Logran and MacDonald lexicon, where they were essentially categorizing words in different bins, like litigious words, positive, negative words, and so on. We take that dictionary and we associate a number, a score to that with the human annotation. And then a second main feature of our algorithm is that it's aspect-based. What does that mean? It means that given a certain text, we will compute the sentiment of that text with respect to a specific token of interest, a topic of interest that is decided by the author itself, by the user. And how do we do that? Well, we do that using a set of semantic rules that actually map what is happening in the sentence and try to identify only the part of the text that relates to the topic that the user is interested in. Now, in just 2 slides, I will try to give you some details about this sentiment analysis tool. We follow a standard natural processing pipeline, natural language processing pipeline, where we do tokenization and lemmatization of the words. So we move the words to their base form. Most importantly, we tag each word with its part of speech and its dependency using the Spacey Python package available online. What does that mean? It means that we are able to identify with the role that is played within the sentence and how does that word relate to all the other words that we have in our text. Then we do things like negation handling, tense and location detection. And once we are able, and once we have this clean text, we are able to apply a set of semantic rules that will identify only the part of the text that relates to the token that we are interested in. And once we do that, we are able to attach to each word a sentiment based on our dictionary. Now, maybe these 2 slides were just a lot of words put together. So let's see an example of that. Let's see how we actually compute these sentiment indicators. Well, we take data from the Dow Jones Data and News Analytics platform. The articles are from 1996 till March 2020, and we have different DNA categories ranging from commodity and financial markets to industrial news, but also general and political news. We have approximately 23 million articles for the major European outlets. So we consider the 4 biggest European countries: Germany, Spain, France, and Italy. And as you can see, we have the most important newspaper. For France, we have Le Monde, Le Figaro, Les Echos, La Tribune. For Italy, we have Corriere, Il Sole 24. So we have a general purpose newspaper, but also outlets that focus on economic and financial news like Il Sole or Les Echos. given this data, we apply our sentiment analysis algorithm and compute 6 indicators of economic sentiment that try to capture different aspects of the economic activity in a specific country. We will have an indicator about a general search for economy, one about the financial sector, one about inflation, industrial production, monetary policy, and unemployment. So let's see an example of how actually the algorithm works. This is a sentence that appeared in Le Bon. So it's a French newspaper on September 9th. The center, of course, was French. Our algorithm, unfortunately, works only with English. So what we did is that we have to rely on a neural network translation machine provided by the e-translation services within the European Commission. We also tried other type of translation tools like AWS, Translate, and so on, and we got very similar results at the end. So the English translation of the sentence here is: the French economy has been experiencing its worst recession since 1968, while Italy entered into recession with a GDP drop, and then it goes on. So in this sentence, we want to compute the sentiment about this token of interest, which is economy in our sense, in our case, and then with the location France. So the algorithm will directly recognize that only the first part of the sentence here in bold is talking about the French economy, while the second part is talking about the Italian one, so it will discard it. And we'll identify a specific rule, a semantic rule. In this case, the rule is that the token here is associated to a verb followed by a direct object. This is a very simple rule, of course. We have also more complicated ones and combination of those rules in our algorithm. So given that it identified the rule that is of interest here and that is characterizing the token of interest, we can attach a sentiment using our dictionary on to all the words in the sentence. So here we will have a sentiment for experience, worst, and recession. And overall, we can compute the sentiment, which is in our case minus 0.92, sorry. So you can see that we have a very negative sentiment for a sentence that actually is quite negative. Here below in this picture, I'm reporting the part of speech and dependency tagging that we do via Spacey. As you can see, we have that each word has its part of speech and dependency attached to that, so we know the role played by the word within the sentence. So as you can see, this is a very the two most important advantages brought by this analysis, by this sentiment tool analysis, is that first of all, we know where the sentiment comes from. Okay, so we can create a narrative about our sentiment, how we compute it or not. And from a policymaker point of view, this is extremely important because we can sell our sentiment indicators more easily and we have a better grasp of the reason why we observe certain movements or not. And second of all, it's really important to have a number associated to our sentiment, to have the sentiment expressed on a scale of -1 and 1.
5 minutes, Luca.
And this is the results for us. Yes, and this is the results, for instance, for Spain, where we are reporting the sentiment indicators for the different token of interest. As you can see, for instance, here in the first panel, we have the economic sentiment indicator. You see that we are tracking quite well the double-dip recession experienced in Europe. Now, we have the 3 data sets: macroeconomic, survey-based sentiment indicators, and news-based sentiment indicators. Let's predict the Euro area 19 GDP. We will focus on the first release. We have an expanding window as of 2015 first quarter, and we will make a forecast with different forecast horizons ranging from 1 month until 2 years. And we will consider real-time information in our model. We built 4 different factors using a different combination of the data sets that I presented you before. We will have one factor built only out of macroeconomic information, the second one here built with macroeconomic information and news, the third one including news, well, the second was about surveys, I'm sorry. And the fourth factor includes all the information available. We have macroeconomic, survey-based sentiment indicators, and news-based sentiment indicators. Given these factors, we feed them into a very simple forecasting model, which is in this case a univariate autoregressive model with exogenous factors. Here in this equation, I'm essentially reporting that. As you can see, we have lags, both variable, which is in this case, the factors that we built in the previous slides. We have, of course, mixed frequencies. So we adopted a restricted Midas approach. And for the order selection, both of the endogenous and exogenous lags, hierarchical sparse penalty, where we are able to automatically select the optimal lag. So let's see some results. Here we have the results of the different models of the autoregressive exogenous model relative to the AR benchmark. I'm reporting so the mean squared error of the different models that you see here in the legend relative to the AR, the red line here at 1. So if you are below 1, the model is doing better than the AR benchmark. We are focusing only here on a point forecast for 2020 Q1. And as you can see on the x-axis, we have the forecast base, so the moment in time where we're making the forecast. As you can see, for forecasting as of a long horizon, we see that there is no real advantage of having a factor including news and surveys. However, once we get to the nowcasting period, so at very close to the release of 2020 Q1, we see that news-based indicators like here in green or in yellow are doing way better than the survey-based ones, which seem not to capture timely the events that will happen in 2020 Q1, which of course was a very hard task to forecast. Now this is a point forecast. Let's make an average of let's make an average of all the forecast measures using the expanding window approach. So here we have again the forecast accuracy relative to the AR. So if we are below 1, we are doing still better than the AR benchmark. On the x-axis, now we don't have anymore the days, but we have the months before the release, so the horizon over which we are making the forecast. As you can see, survey-based sentiment indicator seems to give an advantage here in forecasting, but when we get to the nowcasting tool, still they are doing way worse than the AR benchmark. However, news-based sentiment indicators that we include here in the yellow one, here and nowcasting periods seem to do quite well, okay? On the contrary, as I said, survey are really deviating from the AR benchmark performance. Now, if I want to see whether we have a significant result or not, I can do a very simple Dibble and Mariano test. This is a one-sided test, so if we reject the null hypothesis, we can say that the model in analysis is doing better in terms of predictive accuracy rather than the AR benchmark. And here I'm reporting the p-values of those models at the different forecast horizons. I know that this is not the proper approach from an econometric point of view. If we had a running window, I would have opted for the Giacomino-White version of the test. But here for an expanding window, I couldn't really figure out what to do better. So I just went for the standard Dibble and Mariano. And looking at the results, we see that, yes, looking at the results, we see that, for instance, we have quite significant results here for survey-based sentiment indicators, okay, that do well in forecasting, which is quite striking because we would not expect that. However, models that include news here in the first two panel do not get any significant results in the nowcasting period. And this is a bit disappointing because we were seeing that on average that we're doing better than the AR benchmark. And the explanation for that is quite simple, actually. If we go and look at the same graph that I showed before with their expanding window results here, what I'm adding here is the interquartile range of the forecast accuracy performance around the average performance of the model. I put everything in gray except the AR model with news. As you can see, once we get to the nowcasting period, the average is doing quite well. Indeed, is way below the AR benchmark. However, the forecast accuracy performance is associated to a very large deviation. So news are very helpful on average, but their performance is very, very volatile. So in certain periods they're doing well, and for other forecasts they're doing worse than the AR benchmark. And this is why we don't get significant results for the Di-Bologne-Mariano test. So concluding, we are making a forecast of real GDP for the Euro area 19 using factor models built out with real-time macroeconomic variables, survey-based and news-based sentiment indicators. News-based sentiment indicators seems to have an added value nowcasting, but the improvement is not significant for what I just said. Survey-based sentiment indicators, on the contrary, seem to suffer from poor timeliness. However, in forecasting, quite surprisingly, they have a gain. The next step of our analysis would be to focus on quantiles and see whether actually the gain that is brought by news-based sentiment indicators might be associated to a specific quantile. So maybe what also Tommaso was saying in the previous presentation can be true here. So maybe news-based sentiment indicators are only important during recessions or during large expansions. So these are the slides, the references that I pointed out in the slides. Thank you for your attention. And if you have any questions, I'll be more than happy to answer them.
Okay, thank you, Luca. We have time for a quick question to Luca. Any questions? Also through the chat. Okay, Greg, go ahead.
Thank you for the presentation, Luca. I really liked it. So I would have one question. Can you somehow quantify how, to what extent this kind of negative or not so positive result is due to estimation uncertainty? So what I see is that you have a fairly short sample, which is also kind of plagued by some very unusual events, like big recessions and all that. So I'm just wondering, you know, if there is some instability that you know, seem to be missing, perhaps, or you know, just along these lines.
Yeah, no, of course we have big shocks in our time series, and the idea of having news-based sentiment indicators goes exactly in that line. I mean, news should explain you the uncertainty that is associated to the to our market variables that we want to forecast. So yes, and also the results that I was showing you at the end, given the high deviation of the forecast performance accuracy in the nowcasting period goes along really with this point.
Yeah. So what I was wondering about is, you know, maybe if there is some considerable parameter estimation uncertainty or some instabilities in the and let's say in the new nowcasting period related to the news, then this might partially explain this large variance. So you know, by being able to sort of bring down the estimation uncertainty, you might actually be able to sort of maintain the relatively you know, low spread of the forecasting performance that you showed before the nowcasting period.
Yeah, that I see. Yeah, what we did was trying to have different type of aggregations with respect to the new space indicators that we tried indeed, because of course we compute those daily. And if you look at the daily series, we have a really volatile series. And this was a comment that also came out yesterday in the presentation in another session by Massimo Guidolini and Laurent Ferrara. Different type of aggregation can be explored, for instance, or different type of smoothing. Here I'm doing if I remember well, a 30 days smoothing, okay, in order to try to remove a bit of uncertainty around these indicators. I mean, we can of course explore something, but this is, I think it's a very empirical question. I mean, it's really try out and see whatever you get better and see whether they actually improve the estimation of the models. But thank you for the point.
Thank you.
Okay, thank you. I would like to tell you that after this session, we have the MacroFor coffee break. You can ask more questions there to Luca. It's going to be the virtual coffee break of the MacroFor section that Laurent Ferrara and Greg Ganis and myself are having with you. So please come along, and I'm sure Luca will be very happy to answer any additional questions that you might have. Okay, now is my turn. Let me, okay, go. Okay. Did you see my screen? Do you see my screen?
Yes, perfectly.
Yeah. Okay, this is common work with Eva Senra and Juan Bogalo, both from the University of Alcalá. And what we would like to do here is to disentangle common and idiosyncratic fluctuations when analyzing multiple time series. How do we do that? Okay, so we are going to face a problem of signal extraction in a multivariate context. In that framework, we are able to distinguish between what is common and what is idiosyncratic for any time series. We are going also to relate the signal extracted in a multivariate fashion with the signals extracted in a univariate fashion. And comparing these two is how we are going to assign which part is common and which part is idiosyncratic. And in order to do so, we need to introduce a new signal. It's a new version of already existent signal extraction technique that is called singular spectrum analysis. Okay, I'm going to skip the references there, and because I'm a little bit short of time. And but just to remind you that we are in a problem of signal extraction. And we are going to do signal extraction through principal components. Here we face a difficult question, which is when you extract signals through principal components, you don't know at which frequency those principal components belong. So we would like to identify the frequencies related to the principal components, and in particular, if there are some components, some principal components that are associated to nearby frequencies, we would like to group them in order to form aggregate trend, cycle, or whatever component we are extracting. Okay, so how do we do that? Using singular spectrum analysis, which is an algorithm in 4 steps. First step, build the trajectory matrix from the original time series. Second step, find second moments of the trajectory matrix, and then the eigen decomposition of this trajectory matrix. Third step, group extract the subcomponents if they are related to the same unobserved trend or unobserved cycle, and then reconstruct the cycle or the trend, because you extract them as a matrix and you would like to have them as time series, as we are usually familiar with. Okay, so first step, build a trajectory matrix. So we have M time series, capital M time series, and we put our M time series into a matrix as to selecting window length L and putting just the first L time series, L data points there of our time series. Then we move to the second block of this second column of this matrix, and then we will shift the time dimension 1 point, and we will have our time series shifted to 1 data point, and so on, so on, so on. So for instance, the time series and time 2 appear twice in this matrix. Here you see them highlighted in red. The third data point appears 3 times, and as we move, data points appear more times. This is important in order to reconstruct the time series, the unobserved components that we extract. Okay, so after building the trajectory matrix, which are just the time series and their lags, we find the second moments and find the eigen decomposition, and we are able to project the original trajectory matrix into the sum of matrices of dimension 1 associated linked to the eigenvectors. Okay, good. Then if some of these eigenvectors are associated to the same unobserved component, let's to say the trend, or let's to say the cycle, we would like to group them. And after doing that, we will recover the unobserved trend, the unobserved cycle, the unobserved seasonality, averaging these matrices of dimension 1, averaging the elements appropriately, taking into account how many times and when do they appear in these matrices. Okay, so what is this? Is basic. This is Toeplitz circular spectrum analysis. And what is our contribution? Our contribution is to replace the covariances matrices by a block circular matrix. And how do we do that? We do that by plugging, instead of the autocovariances of the series, a weighted average of them. With this weighted average of them, we are able to build a matrix of second moments that is block circulant. And why this is important? Because this block circular matrix has known eigenvalues and eigenvectors, and we are able to block diagonalize this matrix, but furthermore, we are also able to diagonalize within each block. And the curious thing is that the blocks that appear in the diagonal are the cross spectral density. Actually, it's the cross spectral density evaluated at particular frequencies. So this is very good because we are able to associate the eigenstructure of the matrix with frequencies, which is the handicap of principal component analysis. So solve the problem of associating eigenvectors and eigenvalues to frequencies. We are able to assign a frequency to each unobserved component that we recover. Okay. We have several results dealing with the asymptotically equivalence to our proposal to other already versions of singular spectrum analysis that are already available in the literature. But furthermore, we have an important result that is that allows us to disentangle what is common and what is idiosyncratic in these fluctuations. And this is that for instance, the cycle that we extract from the univariate analysis of one series is equal to the sum of the components associated to the cycle for a particular series when we extract the component in a multivariate fashion. This result, for me at least, it was a little bit surprising at the beginning, because if you are familiar of doing signal extraction with the Kalman filter, the component that the unobserved component that you extract with the Kalman filter, of course, depends on your information set. Because it's an unconditional expectation. And here, the intuition behind this result is that our filter is just has a constant. It's just a filter. It has constant values. So wherever the fluctuation is, for instance, linked to the business cycle frequency, whatever that fluctuation is the same if I extract it in a univariate fashion or in a multivariate way. So if this is the same, why is it important doing in a multivariate way? Well, it's important in order to disentangle what is common and what is idiosyncratic. And let me show you through an application to commodity energy prices. We have a sample running from, monthly sample running from the beginning of 92 to the February 2020. These are the graphs of our energy commodity prices. We have 2 coals, we have 3 oils, we have 3 series associated to the prices of natural gas, and then we have propane. If we apply our analysis computing second moments through this circular matrix, and if we find the eigenstructure of this matrix of second moments, we end up with the following results. First, the trend explains around 53% of the total variability of this series. The cycle, which we associate to a length up to 8 years, explains around 20%. So with the sum of these 2 components, unobserved components, we explain close to 75% of the variability in this series. Okay. Since we were able to, within each block, further diagonalize this block, so at the end we have a full diagonalization, right? We are able to compute not only the associated trend or associated cycle. Here you have the graphs for all the series, the associated unobserved trend, and the contribution of the component within each block, only the first subcomponent, which is in the dotted red line. So as you can see, for most of the series, this first subcomponent is very close to the blue line. The dotted red line and the blue line are very close. So this first subcomponent explains almost the trend on all series, but in US national gas, that you see the red and the blue line do not go together. Okay, so within the trend, what I just said before, the first block, 9×9 block within this second moment matrix, diagonalizing this first block, we are able to disentangle what is due to this first sub-eigenvector. And for the trend, for instance, the first sub-eigenvector explains 80%. And you can see here in the second table, or in the third table, the variability explains by this first eigenvector of the trend for the trend with its series. It's a little bit confusing, but just keep the idea that you can not only block diagonalize the full matrix, but within each block, which corresponds to a particular frequency, you can additionally diagonalize each block. And as I was pointing out before, the first component does not explain the trend in US gas. So since I'm running out of time, just comparing the univariate extracted component with the multivariate extracted component, and seeing the share that is explained through each one of the eigenvectors, you are able to disentangle which part is common and which part is idiosyncratic. Finally, another feature is that, for instance, this extraction was made with a window length equals 96. And here you have the components of the first eigenvector. We have 96 data points. Here you have the components of the first eigenvector. This is associated now to the block corresponding to the cycle, and which is nice to see here is that you are able to distinguish the cyclical position, the cyclical relative position among the series. Okay, and just to finish, we are just proposing a new variant of multivariate circular and spectrum analysis, and we are relating its extraction with the univariate case in order to understand which is common and which is idiosyncratic doing the extraction. Since we are able to do this for each frequency, we are kind of performing in a non-parametric way a factor analysis. And the nice thing here is that we are able to relate principal components with frequencies. We come from a result from the 70s in multiple time series. So the result is not ours. We are just using this result. And what is next and pending work is just precisely forecasting. So hopefully we'll come next year with some forecasts from the technique, but we are thinking still about the problem of forecasting. So this is all from my side, and I will be also happy, I'm sure that Eva as well, to take any questions that you might have. Okay, if there are no questions, we can move to the coffee break for the MacroFor section. Many thanks to all of you from being there, from being here, and I hope to see you also in the coffee break for the MacroFor session. We are just about time. Okay. Thanks to all of you for the participation.
Thank you.
Bye-bye.
Thank you, Pilar.
Okay. Bye-bye. Bye.
Bye.
Bye.